do we create the energy we need? In our case, we're interested in energy for muscle contraction, but these systems also create energy for everything else that we use it for. Okay, so it's not just muscle contraction, that's just where we're focusing so that we keep our head on applied. Remember to check the objectives, okay? And think back to your biology, probably in school, that we use plant and animal products as a fuel, and we do a chemical conversion of energy that's stored in the plant and animal product, and we convert that into energy that we can use within our body. Right? So the fancy term for that is bioenergetics or metabolism. And ultimately, energy comes from the sun. So when we're breaking down energy bonds in plants and foods, at some point, if you follow that line back, there would be energy from the sun. We have chemical energy, electrical energy, heat energy, mechanical energy. So when we digest food, we create heat, we release heat as a form of energy. We create mechanical energy by moving. We have chemical energy transfer. So this is all stuff that you would have covered in school. We're looking at how do we convert all those energy, all that available energy into something that we can use. Alright, so our first energy source is carbohydrate. That's the first substrate that we're going to discuss. And if you're a chemistry person or a biology person, that's what a glucose molecule is made like, right? Personally, I don't care. So that's what a glucose molecule looks like, all right? It's there for those of you that are interested in that. Also, you do want to pay attention to look at the number of carbons that we have in a carbohydrate, all right? Because the number of carbons in a molecule ultimately drives how much energy we can get from that molecule. Okay, so we're going to come back to that idea of the number of carbons. You don't need to learn what a glucose molecule looks like. Okay, it's there just to help you think about what we're talking about. Carbohydrate is very useful for humans because it's a rapid source of energy for us. Okay? It doesn't take very long. It's not a very big molecule. It doesn't take very long to break it down and get at the energy bonds that are in a carbohydrate. So it's very quick. Typically we have some glucose in our bloodstream, so we have some immediately available to our muscles. We also store carbohydrate in the form of glycogen in our muscle tissue, so it's right there where we need it, when we need it. Carbs can be monosaccharides, that's the simplest one, a disaccharide, or a polysaccharide. So the polysaccharides, the starches, are very useful. And glucose, fructose is fruit sugar. Galactose is milk sugar. All right, so there's just different forms. Sugars, starches are all carbs. Potatoes, rice, oranges, broccoli. They're all carbs, but they're different. The starches are not the same type of carbohydrate as the fruits and vegetables. So we can make glycogen. We want glycogen because we're going to store it. Right? We can't, the only glucose we can store is the little bit that we carry in our bloodstream. So glucose isn't useful for storing across the day. Okay? If I'm making glycogen, the fancy term is glycogenesis. If I'm breaking glycogen down because I have it stored and I need to break it down into glucose to transport it around the body, then the fancy term is glycogenolysis. That's not the right way to say it. Okay. So, carbohydrate in the form of glucose and glycogen are important for us for metabolism, for energy production, whether we're at rest, so as you're sitting here or as you're asleep, or whether you're exercising. Okay. If I put lots of these glucose molecules together, okay, then I get a glycogen molecule. So I'm either going to metabolize glucose when I eat it, or I'm going to stick glucose molecules together and store them as glycogen. We store it either in the muscle tissue itself, right, or in the liver. So those are the two places where we keep it when we've got the pantry stocked up. A fat molecule, right? This one's a relatively simple one, only has 18 carbons in it. It's a stearic acid. Okay, again, we don't have to learn the molecule. I'm just trying to show you the difference in the number of carbons. Okay. So when I look at a fat molecule, we can break fat down and use it as an energy source. So fat can be an energy substrate as well for us. And we can find fats in plant tissue or in animal tissue, but nuts have high fat content, some beans have high fat content. Right? So it's not only animal products that have fat in them. And the two terms, when you're looking at fats, the two terms that are important from an energy production point of view are the fatty acid and the triglyceride. So the fatty acids are bound together to make the fat. And then the triglyceride is the storage version. So it's the equivalent of the glycogen for the carbohydrate. I store carbohydrate as glycogen. We store fats as triglycerides. Okay. So when I'm storing triglycerides, mostly we store them in specific sites, fat cells that are made for holding them. We have some in our muscle tissue. You know, if you get a good steak, it's got that marbling, that's the fat in the muscle tissue. But mostly we store our fat in fat cells. So when we're looking at our obesity and our overweight issues that we were talking about in the body composition, what we see is an abundance of fat cells with a lot of triglyceride stored in them. So the primary storage is in a fat cell, and triglyceride is a glycerol plus the fatty acids. The fatty acids are the way we shift it around. We break them down into fatty acids, we use them for energy. Bless you. Something in this room does not agree with you. It's dust in the carpet or something, right? If we have it stored, then if you look at the size of that molecule compared to the carbohydrate, it takes longer to break this down to use it for energy. Right? So carbohydrate is a quicker source of energy for us because it's a smaller molecule. Fats are very, very big molecules, so they can provide a lot of energy, but it takes a little bit longer to get at it because I've got to break down the molecule to get at the energy bonds in the molecule. So it just takes longer, but it means they're a very, very good source of energy for us. Oils, there's lots of health benefits to having good types of fats in your diet. Right? You don't want too much saturated fat, you want more monos and polysaturated fats. Okay. If I use a lot of olive oils or eat a lot of avocados, yes, they're fatty, but they're actually shown to decrease your blood cholesterol levels. So there's good fats and bad fats. We don't want to cut the bad fats out altogether, because saturated fats includes cheese and meat. Okay, I'm not going to give those up, but we want less of those and more of the monos and polys. So if we look at energy storage in a human, then we're looking mostly at carbs and fats. We'll talk about proteins in a minute. Then I'm looking at a carbohydrate of 625, around 625 grams. That's somewhere around 2,500 calories. This individual that these numbers are based on is someone who is 143 pounds with 12% body fat. Male or female? Good. Right? Probably male, because for a female to be 12% body fat would be really, really low. Really low. Right? So this person is probably male. He's either not very tall or he's very lean, right? Pretty small, because 143 pounds is not very heavy. Okay? But this is someone who's in pretty good shape, because 12% is very low. Even for a guy, that's quite low. Okay? So this is someone who is not overweight. This is someone who is lean, fit. Somewhere around 2,500 calories of carbohydrate. Okay. When I look at stored fats, I'm looking at almost 75, 73, 74, yeah, almost 75. Right? A lot of fat. And this is 12% body fat. And we have thousands upon thousands of calories of energy stored. Okay? So running out of energy, if I'm running out of fat, is not feasible. You'd have to be in serious, serious trouble. You're either starving yourself or you're stuck on a mountain. Right? You would have to be in serious, serious trouble to run out of fat stores. Like dying trouble. Okay? Running out of carbohydrate, though, happens all the time. Especially when we exercise a lot. So those days when your legs feel really, really heavy, those are days that you're a little bit low on carbs. So we want to keep an eye on that idea. Most of our carbs are stored in our muscle, but we have some in our liver and very, very little in our bloodstream. Right? That's not a storage. That's a transport mechanism, not a storage mechanism. Okay? lots and lots of fat. Most of it is either under our skin or around our organs. We have a little bit in the muscle tissue itself. So what about proteins? Right? Proteins can be used as an energy source. Proteins are typically not used as an energy source. So when you read, oh, you should eat this protein, you should take this protein shake, you should buy this protein bar because it will give you energy, that's a load of media twaddle, right? Because most of you, particularly you guys, could, well, other than Carlos, how much running do you do on top of your soccer? Not a lot, yeah. You're built for a run. Most of you guys then, unless any of you are training for a marathon or a 24-hour race or the Tour de France, no one in this room does training where you're using protein as an energy source. So be very, very cynical when people are trying to sell you protein as an energy source. That's not what you use it for. We use protein as a building block. It's the bricks for the house. Right? Every time I exercise, I tear little bits of muscles and tissues and connective tissue, and I do damage. If I break the window off my car, what do I have to do? Replace the car, replace the window, right? Well, the same thing happens in our body. If I tear something, if I expect to go back to the gym and train the next day, then I've got to be able to mend the tear. Otherwise, the next day I just do more damage. Right? So every time I do some damage, I have to fix it. If I want to grow, I have to have building material. When we're children, we have to grow because we go through puberty. We need a lot of building material. That's why kids, particularly guys going through puberty, eat their parents out of house and home. Okay? Because you need so much building stuff, you can barely get enough in for the amount of growing that you're doing at that time. Okay? If I want to put on muscle mass, if I want to grow muscle, then I have to have building blocks, I have to have protein. But we don't use protein for energy on the whole. If I run a marathon, even if I'm good at a marathon, you're still looking at, what's the world record for a marathon at the moment? Something silly like 2 hours and 8 minutes or something ludicrous. For most of us, we're looking at 3 or 4 hours worth of work without stopping. If I run a marathon, in 3.5 hours, somewhere between 5 and 10% of the energy that I needed to run that marathon came from protein. It's not very much. Right? Very, very little energy comes from protein. So just be a little cynical, because right now, particularly right now, in this particular era of time, they are trying to ram high-protein diets and high-protein bars and down our throats at every turn. Right? You can't walk through Walmart or flick through a magazine right now without someone telling us we should be eating a high-protein something or other. And very many of them associate high protein with energy. That's not what you're going to use it for. If you choose to eat it, you're not using it for energy. Right? So, proteins are made of amino acids. Hopefully, if you've done your biology stuff, this is all just review. Right? Proteins are made of amino acids. Amino acids can be divided into two subcategories. The first one is our essential amino acids. That means that we can't make them for ourselves. There's no way for the human body to synthesize an essential amino acid. That means I have to eat it in my diet. The other group are non-essential, and they're non-essential because given the right tools, we can make them for ourselves. So I don't necessarily have to make sure that I'm eating them, because I could make it if I need it. Right? Okay, so I've got carbs, I've got fats, I've got proteins. I've eaten these food sources, and I'm going to break them down for energy. We have enzymes, another kind of molecule that facilitates getting at the energy that's stored in these foods. It doesn't cause it, but it helps us out quite a lot, right? So they make chemical reactions in the body work a little bit quicker and a little more efficiently. So they enable us to break down the food substrate a little faster in whichever particular way we're doing it, so that we can get at the energy a bit quicker. Enzymes work in a lock and key mechanism. So that means that one enzyme has a particular shape, and the thing it's going to help the chemical reaction with has a particular shape, and they fit together. So enzymes are very, very specific. They are not generalized. I don't use enzyme A to do job T. Enzyme T has to do job T. Enzyme A only does job A. Right? They're highly, highly specific. They're pretty fussy little so-and-sos, right? But they don't cause the effect that we're seeing in the chemical reaction. They're facilitating. That's an important point to remember. Oops. So, when I'm looking at molecule AB, and I want to break molecule AB down into molecule A and B, then there would be enzyme that helps that occur. Right? If I'm short on that, and along comes enzyme F, that can't do the job. Right? It can't help out. It has to be the right one. When we're looking at the pathways that we break down these substrates, that becomes quite important, because there's lots and lots and lots of different enzymes involved. Review should be review, because everybody's got Biology 207. There should be review. Any questions on that? Good? Makes sense? Kind of sounding familiar? Hopefully. Oops. All right. Enzymes are very, very specific, very, very fussy. They like a particular temperature and a particular acidity level. And they're all different, right? But they all work within a particular range. So that when we start looking at how we do this when we exercise, we start to see some of the problems that all that heat that we make when we exercise can cause energy production. So I'm going to make energy. I've got my carbs, I've got my fats. I'm going to make some energy. I'm going to move around. I'm going to go for a run or a bike ride, or I'm going to play basketball. How do I actually get the energy that I want? Right? So I can do it aerobically. If it's aerobic, it means that you had to use oxygen to make the energy that you require. If I'm making energy aerobically, then I've got byproducts of carbon dioxide and water. But those are good byproducts to have because they're not toxic and they're easy to get rid of. We use aerobic metabolism for things that take a long time. So sleeping at night, sitting listening to me wittering on about XFIT, right? Things that take a long time and have to sit for a long time. We use aerobic metabolism to do that. We also then use aerobic metabolism because if I'm doing it for a long time, I can't be working really, really, really hard. So we also use aerobic metabolism for things that are lower on the intensity scale. Right? Moderate and low rather than really high intensity. So, if I'm looking at what we're interested in, if I'm looking at sports skills or activity skills, then I'm going to use aerobic energy production for running, for walking, for biking, for swimming, for doing an aerobics class. That's why it got the name aerobics. Okay. For a spin class. Walking your dog. Anybody remember to walk their dog? Walk your dogs, good. Walk your dogs. Good aerobic metabolism. You can write it in your physical activity log. Okay? So, if I'm doing work that uses aerobic metabolism, in layman's terms, we tend to call it aerobic exercise. That uses carbohydrate as an energy source and fat as an energy source. Very rarely protein as an energy source. Rarely. If I am not making energy aerobically, because aerobic metabolism provides energy for things that take a long time, and sometimes I do things that don't take a long time. Right? So if I ask you to stand up, stand up. How long did that take you? Other than the delay because you all thought I was pulling your leg. Right? How long does standing up take? 2 seconds, if, right? So, standing up is not aerobic because it doesn't take a long time. Okay? So, I must have another way of making energy that doesn't take a long time. And when we make energy quickly, we don't use oxygen, and it's called then anaerobic, not aerobic. Okay? When we make energy anaerobically, our byproducts are carbon dioxide and lactic acid, actually lactate, but you'll see some lactic acid. In reality, chemically, lactic acid and lactate are not the same molecule. in everyday language, we tend to intersperse those two and use them interchangeably. It's not the best way to approach it, but we've kind of got into the habit of doing that. So often when we say lactic acid, what we mean is lactate. Right? Lactic acid, lactates change the pH in the muscle cell because it's an acid. Right? And that has a bit of an impact on how well the enzymes work, because we said our enzymes are very, very fussy about their pH range. And so it can slow down how quickly you can work. It's not the major molecule responsible for that. We'll come back to that. But it does play a role in slowing you down. So if you're sprinting as hard as you can, at some point you're going to slow down, right? You can't sprint as fast as you can sprint for as long as you can go. There's a finite period of time. And even if you try really hard, you're going to slow down. Because at some point, you're not able, the enzymes that help break down food for anaerobic metabolism slow up because of the amount of acid level in the muscle cell. So if I'm producing it anaerobically, I can make it very quickly. I have to stand up. It takes a very, very short amount of time. I can provide the energy to stand up, because you need more energy to stand up. Right now, while you're sitting, there's not a lot of energy being made in your muscle, in your thigh muscle, because you're not using your thighs very much for sitting. But to stand up, you have to suddenly create energy to contract your muscles to stand up. So your muscles are able to switch very quickly from aerobic metabolism to anaerobic metabolism so that you can stand up. One of the problems with this, with the topics for the next few weeks, is that this is all very, very abstract, right? This is all stuff you can't see. I don't have any way of showing it to you other than telling you to stand up and saying, look at the difference. Right? You can't see it. You have to kind of just believe that that's what's going on. And it's happening so rapidly, it's a little bit mind-blowing sometimes. Because you have to contract a lot of muscle fibers to stand up out of your chair. Imagine what you have to do to run down a football field and catch a football. Or chase down a softball. So it becomes a little bit difficult. I know it's an abstract concept, but we've got to try to keep making ourselves remember how it fits back to what we're doing. Right? That's why this is different to 207. Because in 207, they taught you metabolism, but they're doing biology, not ex-phys. They're not applying it to your exercise. So, if I'm working anaerobically, if I'm making energy anaerobically, I can't do that for very long. Right? If you go for a walk, if you wanted to, if you had the supplies, the resources and the time, how long could you walk for? An hour? Several hours? Days if you're a refugee and you have to get away from home and get somewhere safe. Right? Days and nights without stopping. You can walk for a very long time if you had to. Right? If you're sprinting as hard as you can go, how long can you sprint? Minutes? Seconds. Right? You can run pretty fast for minutes, but you can't sprint as hard as you can go for minutes. Right? You can only sprint as hard as you can go for 10, 12 seconds. Right? So, I can make energy very, very quickly if I have to this way. And if I'm sprinting or I'm weightlifting or I'm throwing or I'm doing something that is short, sharp, quite powerful, I'm making energy anaerobically. And the key point is I can only use carbohydrate. You cannot use fats to fuel anaerobic activity. There's no mechanism in our body to use fats for anaerobics. So if I am sprinting, if I am jumping, if I am throwing, I don't use fat as an energy source. If we go back to some of the conversations we were having about body composition then, if I want to change my body fat percentage, I can't do sprinting and jumping and throwing because it doesn't use fat as an energy source. So everything will start to tie together during the semester. All the pieces of the pie will fit together, hopefully, by the end of the semester for you. So to break it down, I'm going to make energy. What's energy? For a human, energy is ATP. ATP stands for adenosine triphosphate, T for tri, 3, and it is literally an adenosine plus 3 phosphate in organic phosphates. Okay. So I can make ATP aerobically, or I can make ATP anaerobically, but if I want to contract muscles, I have to have ATP available. And when I have ATP available, ATP has an energy bond in it that I can access for muscle contraction. So I have adenosine plus a phosphate plus a phosphate plus a phosphate. Okay. And in humans, we've evolved in a weird way because only this last energy bond, we have 2 other energy bonds in adenosine triphosphate, but we can only use the last one for muscle contraction. So we have to have ATP, we're going to break down ATP, we're going to steal that energy to contract muscles, and we'll be left with a DP, you might not be able to see that colour on there. I'm going to have to get some darker pens if we're going to do this filming. A DP plus this just floating around. A DP is adenosine diphosphate, so I've still got 2 phosphates. I've released the 3rd phosphate, I stole the energy and I can contract muscles. Why can't we steal that one and that one? We can't. Why? I don't know. That's not how we evolved. Humans can't get at that. We can only get at that. Right? That's just the way it is. Okay, so when we break it down, phosphates also increase acidity a little bit. So I've got another product that appears in the cells that can impact pH. Right? And when we do this, we also release hydrogen. And hydrogen is the big whammy. Hydrogen molecules are acidic, and when we make energy, we release a lot of hydrogen while we're making it, and when we break it down. So the hydrogen is even more of a problem within the muscle cell than the lactic acid is, because lactic acid is very unstable. very, very quickly changes into lactate, and lactate can be shifted into the bloodstream and moved around the body. So lactic acid isn't the primary problem, hydrogen is the primary problem. I'm going to stop there. Those eyes are starting to boggle. You don't need eyes boggling, you need brains working. Alright, so think through that. Most of that today should have been reviewed. If it wasn't reviewed, please make sure that you look at it again before Friday, because now we have to actually look at the energy systems, and if that bit didn't make sense, the next bit will just make you want to run out and move. Right? Alright? Tomorrow morning, body composition, dress appropriately. You do not want to have to pull your jeans down and look around in your underwear. Personally, I don't care, but you guys are a bit funny about that.